Hello, well, good morning, ladies and gentlemen. Thank you. My name is Ron Singh for Digi International. I'm going to do a presentation today called Cutting the Cable. The premise of this presentation is very much around the idea of if you have never gone wireless before and are considering it, maybe you have products deployed in the field, nodes covering wide areas, but you're using cables. You're thinking about going wireless, but wireless always seems like such a very daunting prospect. So, right. There are many reasons not to go cabled. Obvious one is cost. Copper is very, very, very expensive. Everybody can hear me, can they? Just checking. I can see a few people. Oh, that's right. I was told switch your headphones on or wear your headphones if you're not doing it already. Some people didn't get that memo. Yeah, material cost. I do track the cost of copper for other reasons within our industry, and copper fluctuates, but generally is going up. Material cost is a very big inhibiting factor to going with cable. Installation cost, actually having people putting down cables, either digging up ground, chasing through walls, running them across the ceiling, has an intrinsic cost to it. Maintenance and reinstallation costs. Cabling suffers. It could suffer from water ingress. It could suffer from being attacked by vermin such as rats that are well known for eating at cables, or just an accident. A digger outside a petrol station on the road could dig through and cut a cable that is vital for, say, point of sale communication. So there's always a maintenance and reinstallation cost attached to cabling. And then flexibility. One of the parts of our company sells a lot of boxes which does serial to Ethernet communication, or conversion rather. We sell those by the bucket. And the reason is there are so many factories and shop floors with RS485 or RS232 cabling there, and it costs so much to dig it up and put Ethernet down that people try to come up with creative ways. But ultimately, the restriction, even if you've got those conversion boxes, is the actual medium itself. So cabling is very inhibiting for the idea of being able to upgrade or extend your deployment. But RF is generally considered very daunting. RF design, certainly at chip level, is very much considered a bit of a black art, right? Or dark art, I should say. This presentation, and I normally would take an hour. I'm doing it in half hour, so I'm doing it at some speed. But I will release the whole presentation, which does go into some more detail that I'm not covering here. But we will cover just some basics in terms of block diagrams, and then I'll do a little bit. Obviously, I have to do the obligatory sales pitch at the very end, but that's tagged on at the end. So I will talk about, again, in a sort of a block diagram form, just the basics of going wireless. We'll talk about things like line of sight and frequency and so forth. I'll talk a little bit about topology, whether it's point-to-point, point-to-multipoint, mesh, so forth. And then I will talk a little bit about extending networks beyond this kind of radio system at sub-gigahertz or 2.4 gig to larger geographies or topologies, rather, using basically cellular technology. So, usual starting questions. If you're thinking about going wireless, how far are you transmitting, receiving, what kind of geography are you covering? How much data are you wanting to transmit? Are you streaming, or are you just sampling a few bytes every few hours? How often are you transmitting? Are you literally sampling data from sensors but only transmitting the deviant data or deviations from the norm? So how often are you transmitting, receiving? Are you power supply limited? Is your deployment running off a battery, or is it running off some kind of main supply? What is your open RF line of sight? I'll cover this in greater detail because it's a very important consideration. And then what are your topology requirements? Are you just doing point-to-point, point-to-multipoint, or trying to operate some kind of mesh deployment? So just breaking it down in its simplest terms, you've got a transmitter and you've got a receiver. You've got the antennas, and you do have to take them in isolation from the basic radio and receiver. The antenna criteria is very specific. And then in the middle, you've got the environment, which is your RF, noise, environment, or line of sight, as we talked about. Those are, breaking it down into its simplest terms. So modulation is the way for the transmission to occur. You pick a frequency, that becomes your carrier band, and then you're going to propagate the waves in order to take your information and take it from A to B. And the data is basically transmitted by modulating that within the wave to get over. Frequencies, I'm sure some of you will be aware, is measured in hertz and is related to the number of wavelengths that respond, or cycles in a second. So when we talk about doing an RF design, the key thing that everybody wants to do is maximize the range. Now, the obvious thing to say is, well, I'll crank up my radio so it's transmitting louder or more powerfully. Fortunately or unfortunately, depending on your perspective, transmission power is governed by government, and for very good reason. Usually, regulatory bodies within a government. And it's a very simple reason. If we were all allowed to transmit at unrestricted power, you would be interfering with each other, and more importantly, you'd probably be interfering with emergency services or other vital transmission that needs to be. So transmission power is regulated by government, and it's a bit of a moving target as well. So, for example, in America, they're in the process of updating the regulations around 900 meg transmission. Reason, there's now a lot more drones. Amazon wants to deliver by drones, and if everybody's using unlimited powered radios to move drones about, there's going to be an RF problem. So government regulation is a moving target and does have to adapt to circumstances in the marketplace. I talked about isolating the transmitter and the antenna separately, and again, the antenna gain, the boost that the antenna is giving the radio, is also regulated by government. So there's little control you have on impacting that, apart from being able to take it to the maximum that you're allowed to. What you can impact is your RF reception side. You can increase the sensitivity of your receiving nodes. You can use various filtering to try and remove some of the noise in the area, in the spectrum, that would otherwise upset or corrupt your data. You can look at the environment that you have to cover and see if there are things that you can do about that environment to mitigate some of the obstacles that might be in the way. When we talk about line of sight, there is a difference between visual line of sight and RF line of sight. Clearly, if there's a great big building in the middle of A to B, then you're going to have a problem. But if you're looking across open countryside, you may not consider that two pylons with a wire in the middle might actually cause you a problem for your RF line of sight. So distinction between the two. So to that point, we talk a lot about the Fresnel zone. And the Fresnel zone, which is defined by this ghastly looking equation that belongs on a GCSE physics paper, is used to identify the characteristic of this volume of accessible area that you can transmit unimpeded. And you can see from a few examples there of trying to transmit across a long distance, you need a bigger radius of Fresnel zone, and you also need to be cognizant of any obstacles that are in the way, such as trees or even traffic. And that's why often the fastest way of navigating this is to put great big antennas and get them well above whatever noise or potential noise can be in the way of your transmission. And just to kind of give you some context to that, if we look at transmission in sub-gigahertz, which is typical for long range, or 2.4 gigahertz, which is what Wi-Fi, Bluetooth, Zigbee all use, you can see that even just covering what you would consider to be quite modest ranges require quite significant Fresnel zone radiuses to be able to get unimpeded transmission from node A to node B. And then just considering those two, because in this kind of smaller IoT wireless deployment, we weigh up the two options of 868 or sub gigahertz and 2.4 gig. I will talk about 868 a lot here because sub gigahertz, unlike 2.4 gig, which is a global standard, all Wi-Fi, all Bluetooth, all Zigbee uses it, for sub gigahertz, it is actually regulated by region. So here in the UK and in Europe, the EU, we use 868 megahertz. In the US, they use 900 megahertz. In Brazil, Japan, New Zealand, and Australia, they use what they call 900 megahertz, but actually there are slight deviations. So I think in America, it's like 913 to 917. Australia uses a different one. New Zealand uses a different one, and they are all incompatible. It is illegal to use an 868 radio in North America. It is illegal to use a 900 meg radio in Europe. So you do have to be cognizant of that. But sub gigahertz versus 2.4 gig, there are noticeable differences. For the same power output, you do get more range on sub gigahertz transmissions. You do get better penetration through obstacles such as walls. It is by definition a less crowded frequency band because, as I said, 2.4 gigs already crowded with Wi-Fi and Bluetooth and Zigbee and other ones. And to a degree, because of that, it's slightly, shall we say, government tends to be a little bit more open to allowing higher power thresholds compared to 2.4 gig. There are some limitations. You wouldn't stream video on it. It's got much less power, data transmission rates. It doesn't support all mesh technologies, and I will talk about topology in a moment. So, for example, Zigbee mesh is only available at 2.4 gig. You can't get it on a sub-gigahertz radio. And as I said, you do need to think about regional deployments if you are making a piece of equipment that you are shipping around the world. So I've got a customer who makes a particular piece of garden equipment which uses wireless technology. He ships all around the world, but he has to be, and he wants that longer range, sort of 10 kilometers, but he has to be cognizant that whichever geography he's shipping it to, he can't use the same radio in there. Just to then bring that down, again, I'll just really illustrates what I was just saying. For 2.4 gig, it's globally accepted as the ISM band of choice for shorter distances and high bandwidth, such as Wi-Fi or Bluetooth or Zigbee. And as you go into the sub-gigahertz, you'll see you have those different allocations depending on geography. And as I said, many geographies refer to 900, but it's a lot more nuanced than that, and they are not compatible with each other. And then outside of those sort of closed loop mesh type networks, you then move on to wide area network protocols. All of those, and I will cover this shortly, sit on existing cellular technology. But even then, there are demarcations around the globe. So in Europe, we tend to favor LTE, M, and NB-IoT, although we are taking on Cat1 as well, and eventually Cat4. The Americans are already there with that, but South America, for example, still uses global 3G. So again, you do need to be cognizant of compatibility on that. And then we talk a little bit about topology, and that's how your network will look, how you want your deployment to look. So the obvious and most simple one is point to multipoint or point to point, which is governed under IEEE 802.15.4. So this is, very simple network. A radio can only talk to the adjacent radio as long as it's within range. It can't hop from node to node. So its range is limited. It's very simple. So A there, for example, is only talking to B, D, and E. It can't receive or transmit to F, G, and C because there's no hopping allowed. It can only extend to the ones within range. It's a very, very simple network. But because of that, and because of the lack of node hopping, it's very quick. It's got very low latency. It is a good network for, say, 2 to 30 nodes, if that is your extended deployment. It does suffer from a single point of failure issue. So if, for example, D fails, there's nothing to bridge it there. A will only talk to B, or E and F and G can only talk to each other and any others that are in range. So a D dropping out does have a huge noticeable impact on the whole node deployment. Conversely, mesh networking, and which is the one that, to be honest, most deployments I see, most customers I see using, gets around that problem. It's much more powerful in terms of being able to route data from the farthest point of the network to its equal extremities. It does this by allowing the radios to hop from one to another to get from various points. It's self-routing, so it will look for the most optimal route. Cognizant of the fact that there is a delay because of all the hopping, it will look for the most optimal route, whether that's in terms of number of jumps or number of data transmission that's going through certain other nodes. It will go to ones which have got less traffic on them if it sees it as a faster route to get from A to Z. It's self-healing. That means that if a node fails, it will look at it, recognize that that node is no longer transmitting or receiving, and figure out another route to get from A to Z. We offer two types of mesh. We support Zigbee, which is a global open standard, and we also operate a closed loop standard called DigiMesh, and I'll show you the differences between the two. So as I said there, any radio can communicate with any other radio, even if it's not in range, and it does it by hopping from one node to another. The messages, as I said, are automatically routed. It will discover new routes as it needs to. So if B is trying to get to N, the optimal route is to go through F, H, and K. If F breaks, it will figure out a route to go around the other nodes. If F is suddenly deluged with traffic from other nodes, and therefore it's increasing the latency it would to go that route, it will figure out another more optimal route to get from B to N. Okay, I said, and if a node breaks, I'm repeating myself. Okay, mesh networks can cover really, really large areas. Probably the biggest application that I see is solar farms. So as you can imagine, solar farms are huge, lots and lots of solar panels. They have what they call sun tracking systems. So they're moving it with like a pan tilt system to be able to track the sun. Equally well, the more advanced ones will have some kind of folding mechanism. So if it detects a sandstorm coming, which does horrendous damage to panels, then it folds them up or drops them down or what have you. Those solar farms typically are using mesh networks at 2.4 gig, usually Zigbee. And there's very low latency in Zigbee. In fact, it's better than LoRa in that respect. And they'll use that to manage that. You'd also see that kind of network for, and I can't see it here now, but those sort of green emergency lighting that you have around this kind of building, they don't sit on the network because they could be an IoT point of entry, but they have to be connected. People need to know that they're working properly, that the trickle charged battery inside is operating, and that would typically use some kind of mesh network such as Zigbee. So I said the benefits of a mesh network, very straightforward. It can cover a very large area. You can support up to 1,000 nodes. And again, think about a solar panel farm and each one of them having an independent node operating a pan tilt motor system for it. It does repair itself. It can spot failures in the network and work around them. It's self-heating. It's interesting. I didn't write these slides. It says best for static networks, and that's arguably true for something like a solar panel farm. However, we've got customers who, those kind of the drones with the lights on that do the displays New Year's Eve or whatever and make shapes and all that. They are typically using 2.4 gig, and of course they're not static; they're moving around, and they are able to coordinate each other at quite quick speeds to change shape from, the world to whatever else. And there's always a good level of security. So obviously Zigbee uses a 128 bit level of security. Digimesh uses 256 AES. I just put up a bit of a difference there, a chart there you can see. There's Zigbee, as I said, very well established open protocol, and Digimesh, which is our own closed loop protocol. The most significant differences I would just point out there is that Zigbee only, as I said earlier, runs at 2.4 gig. Digimesh will run at sub-gigahertz as well. And the security on Digimesh is also tighter than it is on Zigbee. And I'll give a really good example of that. I've got a customer who's making equipment which is going to be used in the Olympic Games. So it's being deployed in Paris. They've been using our products for years. It's deployed around the world, not a problem. They put this equipment up in Paris, and it started to get interference. Never had interference before. Turned out it was drug dealers who were using jammers to stop police radio, well, not police radio, but police communication emergency services. So they were able to re-flash all of the modules from the Zigbee firmware to the Digimesh firmware, and they got round it. So, just an example of that, right? So then, obviously, I'm talking about closed loop environments where you not necessarily using a gateway, you're using point to multi-point or mesh networking. When you start to get further into larger ones, so we start looking, and we're only talking about IoT here, there is a need for wide area networks, low power, because we are talking about IoT applications here, that extends beyond the range of what we talked about with sub-gigahertz and 2.4 gig. There are options. Sigfox is there, but Sigfox is dead now. LoRa's still there, but LoRa does suffer from the problem that you have to have your own gateway to support a LoRa network. So the most obvious ones to go with is something that's based on cellular technology. And examples, and I'll talk about them, include NB-IoT, Cat1, Cat-M, Cat4. Basically, the best, selling points or benefits about using LTE technology is you're using something that's already in existence and it's deployed, and it's biodefense by all, notes is global, right? So it's a mature ecosystem of network operators, Vodafones, the AT&Ts, whatever. You've also got a lot of MVNOs, and MVNOs are companies that go around and they sign agreements with individual network operators across different geographies so they can provide you with one SIM card that will work everywhere for an IoT application, whether it's NB-IoT, Cat-M, Cat1, Cat4. You are using infrastructure that's already existing, so you don't have to worry about working out your Fresnel zones and your antenna gains and all that. You're using cell towers. It's very scalable, as I'll show you in a minute. You can go from very, very low data rates on NB-IoT, which is really ideal for static applications, to Cat-M, Cat1, Cat4 for moving applications, such as, we've got customers that will use that for diagnostic equipment inside trucks, where they're driving up and down the motorways and want to be able to track all the characteristics and performance. Very low latency. We're talking about cellular technology. The coverage is excellent, as you can imagine. Very good building penetration, and very low power. We offer 3 today. We've got NB-IoT, we've got Cat-M, we've got Cat1. We'll have Cat4 coming shortly. But just looking at the technical characteristics there, just a few things to point out. Is obviously the data rate, very, very low at NB-IoT. And of course, it goes up to Cat1 and will go up again with Cat4. This becomes very important around FOTA. FOTA is firmware over the air upgradability. And so in your deployment of nodes out in the field, you may need to be able to update the firmware periodically. It could be a bug fix. It could be a security flash. It could be a patch, sorry. It could be a new feature that you're incorporating within your firmware. So you do need to be cognizant of what technology you select, because not all of them are suitable for being able to do, reliable, secure, delivered firmware upgrades that then can be refreshed onto your node, right? And then as I said, there's other considerations there in terms of power consumption. Obviously, Cat 1 and Cat 4 by extension are much more power hungry than NB-IoT. Okay, thank you. Right, so good. Right, right. All right. Okay, I'm there. Portfolio, sales pitch now. We do modules. We do RF modules, right? Many people, engineers I met over the years, immediate go-to is to try and go chip down. Chip down is very, very different. It's very, very difficult. It's a dark art. Putting the chip down, putting a radio chip on a PCB, its performance is impacted hugely by the way you lay out your PCB tracks, microvires between the layers in the PCB, other components, even terminal screws that you've got on the PCB will impact the way that a radio chip works. And unless you've got that in-house experience and know-how, I really would recommend not doing it, right? It's not something for the faint-hearted. If you go with a module, you're offloading that onto someone else. Your module vendor will have picked out all the coexisting components, such as the radio, power amplifier, if it uses one, the timing crystals, and they will do all the design for you, and they will optimize that design and give you that know-how straight out of the box. It works usually pre-certified, so certified for 2.4 gig or certified for global at sub-gigahertz. So that is not, again, to be underestimated, because the test house approvals on that run into tens of thousands of dollars. Bluetooth Zig certification, tens of thousands of dollars. So they're stripping all that out of you. Yeah, you could buy the chip for $2 and the module weighs in at $10 or $15, but there's a reason for doing that. Modular design, hopefully, will apply a little bit of low power intelligence on board. A good RF module should have a microcontroller on there, which you can then do with a bit of scripting in MicroPython, write a little application. Because in an ideal world, if you're sampling data and transmitting, do you want to transmit all that data? Or if you've got a bell curve, do you just want to transmit the deviances either side of that, which of course reduces the power consumption of the module? So should be some kind of onboard intelligence that you can easily use in scripting, right? Hopefully there'll be a really good tool set. And by that, I mean not just an SDK to get it doing what you want, but maybe a mobile app, maybe software that allows you to import a schematic for your deployment, or even images from Google Maps that will help you define what that Fresnel zone might look like. And then hopefully it's coming with a damn good level of IoT cybersecurity built into it. We're Digi. We make a range of modules in a range of form factors, surface mount, through hole, micro mount. They support a range of frequency bands, sub-gigahertz, 2.4 gig cellular. They support a range of protocols, Zigbee, Bluetooth, IEEE 802.15.4. The beauty of our module is whatever you pick, the pin out and the footprint is identical. So you can switch between them. And I really do mean identical. You can start your design with a breadboard and just plug in a through-hole module. When you've got your design working and you want to move to your first iteration of surface mount, you just transport the same pin out and you go for a surface mount module. And if later on you want to respin that and shrink your PC, you can take that same module and go to a micro mount version. It's still the same pin out. It's still the same tracking footprint. You don't have to do a lot of work redeveloping your PCB because you've changed module. Within, say, 2.4 gig, it's actually all the same module which can be reprogrammed to support those different protocols. So as I mentioned, I customer in France who had to reprogram it to get around the drug dealers. It was just a case of reflashing his deployment from Zigbee firmware to Digimesh firmware. And then that footprint, it will support all these other protocols and bands as well. That becomes really important. If you're making a piece of equipment with a PCB and you are shipping it around the world, if you go chip down, you've got to make a different PCB for every geography you're shipping it to. If you go with a module like ours, which has an identical footprint, you just plug in the one you want. I've got to finish now. Oh, and all our modules, we also offer different antenna options as well without impacting the footprint or pinout capability. I won't go into all this, but it's an ecosystem, and all of our products have development kits. They range between $99 and $199, and they're readily available and in stock at all our distributors. Thank you very much for your time. Just finished to get in there, all right? Enjoy the rest of the show. Thank you.